Thank you for reminding me about that. Okay, so this kind of my research path has led me to use Bayesian statistics more and more frequently. And just as a little background, last fall, I was lucky enough to take a 3-day intensive workshop from Roy Levy at Arizona State, who is a quantitative psychologist who focuses on Bayesian methods. So I do want to note just at the top that while I'm becoming more versed in Bayesian methods, I am by no means an expert, and I still have a lot to learn. And this talk is really to share some of what I've learned so far and highlight some scenarios where I have found Bayesian to be particularly useful. And so my hope is that this talk will provide a kind of basic overview of Bayesian statistics and give you an idea of if and when it may be useful in your own work. All right, so as far as what I will be covering today, I am going to try and give you the what, the when, or the what, the why, and the when of Bayesian statistics. So what it is, why you might bother doing it, and when you might use it. Importantly, I am not going to tell you the how today. So this is mostly for the sake of time. And if you all want me to come back and give a how presentation, I'm happy to do that. But it's mostly going to be covering kind of that what, why, and when topics in my presentation today. Okay, so what is Bayesian statistics? And to answer this, I'm going to do something that requires a little bit of audience participation. So I know most of you were here last week when my lab mate Morgan gave a lovely presentation on height perception. And so I know we have at least a few height perception experts in the room, and most, if not all of you, are at least somewhat familiar with the topic. So I'm going to go ahead and launch this poll. And I just want you to intuitively answer on how correlated you think perceptual estimates of building height are with actual building height. So if Morgan was to go and do a follow-up study, she's presenting people with buildings of different heights in her awesome virtual environments, how correlated do you think the actual height of the building is with how tall participants say the building is? I'll give you all a minute to answer. Okay, so it looks like we have a good sampling, so I'm going to go ahead and end this. And I just want to say that congrats, you all are already thinking like Bayesians. You're already doing a Bayesian kind of thinking in this context. And you're doing that in that you have beliefs about how things should relate in the world. And what Bayesian statistics is just taking those beliefs and then formally incorporating them into our statistical analyses. So Bayesian statistics as a whole is a statistical framework. And there's this quote that I really like from Lindley, and it states that Bayesian statistics is not a branch of statistics, it's a way at looking at the whole of statistics. So really any analysis can be done in Bayesian. You want to do a regression? Great. You want to do an SEM, a multi-level model, logistic regression, anything you want to do, you can do within a Bayesian framework. And I like to think about it more as a way of thinking and reasoning and kind of a whole approach to thinking about a way to do analyses. So to fully understand what Bayesian statistics is, I think it's helpful to contrast it with the statistical framework that we all typically work in, which is a frequentist framework. And when we think about the differences between a frequentist framework and a Bayesian framework, the two areas where I see the biggest differences is how they think about probability and inference. So on the probability front, in a frequentist framework, probability is based on repeated sampling under near identical conditions, and that gives us some sort of a long run frequency. Whereas in a Bayesian framework, we have this kind of different conception of probability that's sometimes referred to as a subjectivist probability. And so that's based on a subjective belief quantification or degree of belief, which sounds fancy, but it's really just what I had you do at the beginning of this presentation. It's just what you think about how two things might be relating in the world, or more things, depending on what your question is. And then that belief gets updated as data are observed. And as far as inference, in a frequentist point of view, we are inferring point estimates about parameters. Oh, yes, Corey. Oh, I think you're muted.
I just want to go back to the subjective belief.
Yeah.
Does this take into account not only the belief that you have, but the confidence in your belief?
Yes, and I will get to that question later. So when you're specifying this, which later we'll learn about what a prior is, you're able to say what you think and then quantify how confident you are in that belief.
Got it. Great. Cool.
Okay, awesome. So, and this is kind of a good segue, Corey, because in Bayesian, we are actually, instead of inferring point estimates about parameters, we're actually inferring distributions about parameters. And this will kind of become a theme that we think about a lot in Bayesian, is that everything's a distribution. And we'll have to kind of shift to thinking less about point estimates and more about distributions of things. And specifying a distribution is actually how we're going to express our uncertainty, just to foreshadow a little bit. Okay, so where does Bayesian statistics come from? Where'd this all come about? So in the 1700s, Reverend Thomas Bayes came up with this cool little formula, and it states that the probability of A given B, so that vertical bar just represents given when we're talking about probability, is equal to the probability of B given A multiplied by the probability of B, all divided, or probability of A, all divided by the probability of B. We're going to walk through an example of this, so don't worry too much about the details now. But the really cool thing about Bayes' theorem is it lets us go from the probability of B given A to the probability of A given B. And that's really important because this allows us to go from the probability of our data, given the null hypothesis or whatever hypothesis we want to evaluate, to the probability of the null hypothesis given the data. So this theorem allows us to evaluate the probability of a given hypothesis. And just as a reminder, in a frequentist framework, we can only ever see things about the probability of our data given the null, and we have no ability to evaluate the probability of a given hypothesis. So this is a really cool thing that can be advantageous in certain scenarios. So I'm going to walk us through how this formula works, and I'm going to do so using an example that we all, unfortunately, are far too familiar with, and that is COVID-19 testing. So if I were to go out and get a rapid antigen test, and I look on the box or I read through the pamphlet for that antigen test, somewhere on there, I'll probably find some sort of an accuracy for the test. Accuracy can mean a whole bunch of different things, but most often this refers to what people in public health would refer or call the sensitivity of the test. So that's really the probability of a positive test given someone has COVID. But if I'm going out and taking a rapid test and I suspect I might have COVID, I actually don't care about the probability of a positive test given COVID. What I care about and what's going to help me with my decisions is the probability that I have COVID if I were to test positive. And so Bayes' theorem gives us a way to calculate this. So if we substitute in the components of this example, in green here on the left, we have what we're looking for, hoping to answer in this scenario. So the probability of COVID given a positive test. And we can calculate that by combining that accuracy value, so the probability of a positive test given COVID, multiplied by the probability of COVID in the population at large. So this is sometimes referred to as prevalence, but what percentage of the population has COVID at a given time? And then we divide that by the probability of a positive test. So this is just overall. So just the probability of you testing positive, whether that is a true or a false positive, just all the positives divided by the total number of tests that were given. So we could substitute some numbers in here. One antigen test that I took a couple weeks ago had a 93% sensitivity on the box. And I had taken this test at the height of the Omicron surge, in which the prevalence of COVID was a little above 20%. So it was pretty high in the population. And if I calculate in the false positives as well, I can get my probability of a positive test, which in this case was 0.27. So I can see that my probability of having COVID, given I have a positive test, is 0.76, which is actually a pretty different number from that 0.93 accuracy that was stated on the box. And we can see how this whole formula is really reliant on what these numbers are. So say we bump that prevalence value down to 0.05. Maybe I took this test earlier in the pandemic, or maybe the prevalence among people who are vaccinated and boosted is closer to 5% rather than 20%. And we could see in that case where there's a much lower prevalence of something in the population, it could actually be the case that with a positive test, it's possible that it would be more probable for me to not have COVID than have COVID, even though I had a positive test. And this is the reason why your doctor likely will order a follow-up test if you test positive for something that is pretty rare or has a low prevalence in the population, like certain kinds of cancers. So this is why things like follow-up testing are really important. Okay, so that was all with these nice discrete variables where, I either had COVID or I didn't, and I either tested positive or I tested negative. But we can also use Bayes' theorem in the case of,
What was the 0.27 again? Where did that number?
0.27. So that is, I calculated that. I had to do some digging on the internet to calculate this, but that is the total, given the test, the total number of false positives, true positives divided by the total number of tests administered.
Okay.
So just the total number of positives, whether they're true or false.
In the population.
Yeah, so in whatever was being studied for that test. So it's like your false positive and your true positive rate divided by whatever that sample was.
So in this case, would that number always be higher than 0.22?
Not necessarily. It depends just on the given false positive rate of your test. And that number can fluctuate a little bit with some of these other numbers. They oftentimes move together and they can be kind of hard to pin down. I just kept them consistent in this example for demonstration, but in real life, they might move around. Public health is hard. I don't envy the kind of calculations that they have to do on a daily basis. So, but when we think about moving this into the kind of data that we're more likely to work with, which might have continuous variables in it, we have to make some adjustments, but it is the same theorem at work here. So we have what is on the left-hand side of the equal sign here is always going to be kind of like our answer or what we're looking for. And in this case, our answer and what is in green is now going to be labeled as our posterior. And I'll, again, work through this whole formula in an example. So if it seems a little opaque or vague right now, that's okay. And then that is going to be equal to the what is called our prior, and that's our way of expressing our prior beliefs. Like I mentioned at the beginning of my talk, whatever you believe about how two things or many things may be related. And then that's combined with the likelihood, which is basically just our data. So that's whatever evidence we're observing. And that's divided by this normalization factor. And I don't want you to worry too much about the normalization factor. This kind of just ensures that the math works and our probabilities stay between 0 and 1. We can actually pull that normalization factor out and get rid of it entirely. And the only thing that would change is that equal sign would change to a proportional to sign. So if we get rid of the normalization factor, the posterior will be proportional to the prior and the likelihood. So when we're using Bayes' theorem with data that's a little less like neat and discrete as that COVID example, the math does get a little more complicated and it does get a whole lot more computationally expensive. So there's this quote from Sharon Birch-McGreen that I really like, and she says that Bayes' theorem is a theorem in need of a computer. And I think one reason that Bayesian statistics is kind of gaining a lot of popularity lately is that we finally have the computational power to feasibly run Bayesian models on computers that are accessible to the general public. So only pretty recently has this become accessible to anyone that doesn't have access to like a high performance computing cluster. Okay, so we've looked at Bayes' theorem, we've kind of seen how it operates, and I'm gonna guess that you have questions about one thing in particular. And if I were to guess what you had a question about, I'm gonna guess that it's gonna be about this little component here in orange. What is going on with the prior? What is it? What is it? What is it doing? And how in the world are you supposed to specify it? So what is happening with the prior here? So a prior, like I was talking about earlier, is a quantification of our beliefs and our certainty or uncertainty about those beliefs. And to specify a prior, we need to kind of make that shift to thinking about distributions instead of point estimates. So we need to think about what the distribution of a given parameter in a model we're trying to compute might be. And then we express the uncertainty about that belief through the shape that we decide for that distribution. So we'll walk through an example. Yeah, Corey.
Just to make sure that we're clear, is a point estimate a mean or a median or a mode or something like that?
Yep, any sort of, it's just like a one number. Whereas when you have a distribution, you're specifying, okay, I have this mean, and then this is the variability around that mean. Or it's like skewed this way, or it's really flat or really pointy.
So I'm going to ask a follow-up question to that in that case, because we do count the variability in a frequentist model, right? So I'm not, because I mean, like if you were to plot just a mean without the standard error, that would not be acceptable, right? Like, and in a lot of cases, even violin plots and things like that do show the distribution or what we're doing. So I'm not mentally, I'm not quite making that leap.
Yeah, so part of it is that in frequentists, we are assuming our parameters are like fixed in our population. Like they're over here hanging out, they're fixed, and we're trying to estimate what those are. Whereas in Bayesian, like we're inherently trying to build a distribution about what plausibly our parameters could be instead of our uncertainty of that like estimate and its relation to the population value. Does that answer your question? Okay, awesome. So if we're—
Can I ask a quick question too?
Yeah, of course.
Sorry. So I kind of was thinking, I think the same thing that Corey was thinking. So in building that distribution, do you think about a point parameter first or no? Like, do you have to say like, here's the mean, and then I'm gonna stretch out the distribution to be wide around that mean or narrow? Like,
totally.
Don't you kind of have to have a point parameter first or no?
So, I mean, you could do it either way. It depends. Okay. I tend to do that. I think what is the value I think is most likely, most probable for whatever parameter I'm trying to estimate. And then I kind of build my distribution around that. But I'll talk about this a little later. You can also do this with uniform distributions where you're saying it does every value within a certain range is equally likely. So you don't have to necessarily have a mean that or a point that is more likely than other points in your distribution. But when I'm thinking about it and trying to specify a prior, I tend to kind of think of what could be the most likely and then go from there of what my uncertainty around that parameter estimate is. Does that answer your question, Janine? Okay, awesome. All right, okay. So in specifying a distribution, we could specify something that is pretty tall and pointy, or we could be like platy, the uncertain platypus, which is my favorite mnemonic for remembering what a platypurtic distribution looks like, because it kind of looks like a little platypus bill. And we could say, like, I think this value is a little more likely, but I'm not very sure. I'm going to make my distribution kind of pretty even across, and maybe certain values are just a little bit more likely around the middle. And we can actually, like I was kind of in answering Corey and Janine's question, we can actually do that so much that it's just a flat line across here. And the interesting thing about Bayesian is if we specify a uniform distribution that ranges across all of the possible values, so negative infinity to positive infinity, we can actually approximate frequentist results. So if you have a flat prior that ranges from positive to negative infinity, and you do an analysis Bayesian, you do an analysis frequentist, your estimates, your like parameter estimates are going to be super similar. Like there might be like a tiny bit of error, but they're basically going to be the same there.
So to some extent, that sounds like you're actually adding information into your model that is going to further specify the downstream results, right?
Yep.
Rather like relative in Bayes relative to a frequentist model.
Yeah, so you can pretty much like replicate frequentist analysis in a Bayesian framework. And then that prior and how much information you specify there can just add in a little bit more information. And I'll talk about a little later, like why that can be useful to add in that prior information in certain circumstances. And I'm like by no means saying like you have to go do Bayesian. This is the best framework. Just trying to give you an idea of when it could be useful and kind of the basics of how it operates.
And Miranda?
Yeah.
So basically, I mean, I've always liked this approach because it has a hysteresis in terms of our scientific knowledge. Mm-hmm. That is, rarely do we do a study where there is no prior studies that have been done. I mean, yeah. I fall into this stuff with how risky is, say, talking on a cell phone. And there was a mountain of data saying it was really dangerous. And then one method came out saying not. And that group basically said, let's forget about all the other evidence. And it's like, no, basically, you should have a lot of evidence to say that this earlier work was wrong and not just a 1-to-1 kind of ratio. So I really always think that this approach is really very useful and should be more practical.
Yeah, and that's really what Bayesian's all about. I'll get to this a little later, but it's all about weighting the amount of evidence that we have in a belief. So we have a prior belief and we're then collecting data, and the more data we have, the more weight that has. So it is all calculated in on kind of this weight of evidence that fits pretty intuitively with how we tend to think about science. So, okay, so we have our little platypus distribution here. And I'm going to walk through how we actually might specify a prior and how it will work. I'm going to gather some fake data that I made up, and we're going to see how it affects our posterior. So we're going to be working with some kind of things that are maybe a little easier to think about than like a population parameter. We're just going to be, our research question is we're interested in determining the proportion of people in Salt Lake City who wear masks in public places. So one way we could potentially investigate this is we could go to the Smith's on 800 South and 9th East, or any grocery store in the Salt Lake City area, and record how many people were wearing masks. And beforehand, say that we believe about half of people in Salt Lake City wear masks. And we're not super confident in this belief, but it seems like a pretty reasonable guess. So I might specify a distribution that looks like this. So I have 0.5 as my most likely value there. And then I have kind of a flatter distribution around that. But given I've lived in Salt Lake City and I've both seen people wearing masks and not wearing masks, it's highly unlikely that 0% of people are wearing masks or 100%. So we can almost kind of like rule out those values just based on some like minimal experience and some pretty kind of reasonable beliefs. But this would be a distribution and kind of how we would specify it. So if we were to take that prior, it's in green here again, the scale shifted a little, but don't worry about that too much. And if I'm going to walk into Smith's and I look at the first 10 people I see, 6 of them are wearing masks, 4 of them aren't. So that my data would tell me that about 60% of people were wearing masks. So that is what is in blue here on my slide. The prior is in green, and we can see how the posterior, our answer, is kind of in between those two. So 10 is a pretty small sample size. So let's say we go ahead and collected 50 people, and we get that same proportion. So we have 60% of people in our data wearing masks, so 30 people wearing, 20 people not. And we can see that that posterior is shifting more towards the data, and that's because we have more weight of evidence in our data now. We've observed more things that make us think that that is what is actually happening here. And then, yeah.
So the y-axis is changing pretty considerably. Does that matter, or is that a just a normalized like value that doesn't really matter?
So yeah, it's not going to matter too much in this case. Basically, like the area on the curve always has to sum to 1, and the way that this graphing program in R works, it's going to vary a little bit depending on how pointy the distribution is. But that's not something that's going to be like super important in this example, or in general, not something that you have to spend a lot of time worrying about when you're doing your distributions. You just have to say like, what's your kind of most likely point if you have one, and then what's the kind of variability around that.
But so I guess, is there any, I mean, I guess, what would, if there were a label on that axis, what would the label be?
The label would be just like frequency, I think, in this case.
Frequency, okay.
Yeah, and so these are, because this is proportion, these are beta distributions, and then they have like 2 parameters that are changing how that beta distribution looks.
Okay. This was done in R.
Yes, and I'm happy to share like the code that you can use to generate this if you want to play around with that on your own. Okay, so then say we go ahead and get 200 people now. And we have that same proportion of 60% of people wearing masks. And now we can see that the likelihood, so our data and our posterior are almost completely overlapping, because we have so much weight of evidence in our data that those two start to look more and more alike. And as your sample size gets bigger and bigger, the influence of your prior is going to get less and less.
Hey, Miranda, sorry to interrupt, but I didn't see in those equations how sample size would fit in.
In these equations?
No, the earlier equations you showed us at the very beginning.
Yeah, so it's the math's a little complicated, and I don't feel like I am totally equipped to explain that. Pascal is here, so if he wants to chime in, he surely can. But basically, you're having a weight there where the more you have more of a weight in that likelihood than you do in the prior, and that will kind of outweigh and have more influence on your posterior. Does that kind of
totally makes sense?
Give you enough?
That totally makes sense, but I didn't see a sample size in the equations that you showed.
Yes, I could try and explain it, but I think my knowledge of the math and how everything is operating is, I maybe don't feel totally qualified to exactly how that weighting works, but I believe there is some sort of a weighting mechanism here where as the sample size increases, you're getting more of an influence of your data onto your posterior.
So if it's helpful, I'll just chime in quickly, but I'll try to keep, I don't want to chime in too much, Miranda, as you know. That likelihood is directly parallels what we do in frequentist statistics when we calculate the likelihood. And so the shape of that likelihood distribution will change depending on factors such as your sample size. So for instance, if Miranda only observed 6 people at Smith's, we would expect that likelihood to be relatively wide, much like if you were doing a coin flipping distribution, if you've only flipped the coin a few times, it would be hard to estimate that it comes up with probability 0.5. You would have a very wide distribution associated with that estimate. But as you sit there at Smith's and collect 1,000 people, that likelihood would shift to something much narrower, because you become much more confident about what that proportion of people wearing masks is. In some ways, you could see that, particularly in contrast to the prior, that likelihood, you're much more confident about that 0.6 in some ways, because of the narrower distribution and the higher density on the center of that distribution than you are even of the prior. And so this is the chance for the data to overwhelm your prior, but I think Marinda will go that direction. So
yes. Thank you, Pascal. I appreciate you chiming in there, because that's a good question. And I think that was some useful context on how to fit that all in. Okay, so as we see here with how our prior kind of can have a varying influence as we move to a larger and larger sample size, basically at a smaller sample size, you're having you're drawing more information from your prior, and your posterior is going to look more like a mix, where as you move towards that larger sample size, your posterior will just look more and more like your likelihood or the data that you're observing. So I now kind of just want to talk a little bit about the utility of priors. So in this example, I'm going to say that I survey 1,000 people across every state in the US about who they voted for in the last election. And say I only get 3 people from Wyoming. All 3 of those people voted for Trump. So under a frequentist framework, these 3 people are my representation of Wyoming. But do I really think 100% of people in Wyoming are Trump supporters? Does that really make sense? And in a Bayesian framework, well, we can think about it conceptually in a frequentist framework that might not represent things. In a Bayesian framework, we have a way to formally incorporate the fact that we don't really think that 100% of people from Wyoming are Trump supporters. So in a Bayesian framework, I can use my prior knowledge. I could use voting patterns in Wyoming. I could use the fact that I know people in Wyoming who are Democrats. And so I already have a proof point that this is not the case. To conclude that while there might be a high proportion of Trump supporters in Wyoming, it's also probably not 100%. Okay, so moving on, now that we've kind of described what Bayes is, why might you want to bother with it? So you might be thinking, this seems complicated and like a lot of extra work. And I can confidently tell you that it is. I'm not going to try and like disillusion you in any way. Bayesian requires you to adopt kind of a whole new set of assumptions. And priors are a really key piece to this whole equation, and they can be kind of hard to specify and hard to wrap your mind around, and it forces you to kind of think in a different framework. However, I do believe that work can be worth it. And I think part of the reason it can be worth it is that Bayesian kind of moves you away from your reliance on the like asymptotic assumptions of a frequentist framework. So it's less about the frequentist kind of like, okay, we're going to wait and see about these long run frequencies. And it's more about what can we say now, given what we know about the world and the data that we've observed. Also, as I demonstrated in the example about Wyoming, the ability to build in prior information can be really useful. And then finally, as I hope I'll highlight in the next couple of slides, I find that Bayesian interpretations are often more intuitive and kind of like Dave was saying, can sometimes match your, your feelings about how science and the world should operate.
Yeah, and I just, so I just coming, I'm a purebred frequentist. So
yeah,
when one of the things that I've always, not really enjoyed about some of the stuff we have to do in the statistics related to frequentist analysis is stuff like dealing with power and thinking about, it's not to say that I don't think it's necessary. I absolutely think it's necessary.
Yeah.
And we use effect sizes and make these estimates of the power we need to detect such an effect and stuff like that. For some reason, this gives me Bayes has always given me this kind of flavor of something along that line. Like you're trying to predict something based off of effects from other stuff. Except in a frequency framework, all of that, the effect size, and even in this case, the effect direction, right? Like effect size doesn't take account of the direction of the effect between two different conditions that you're trying to measure. And that, essentially this seems to combine those ideas to some extent by using the priors. I don't know. Would you agree with that assessment to some extent?
In some ways, and I actually I have a slide on kind of like how Bayesian can be used in smaller sample sizes sometimes, but you are kind of combining. It's not like a solution for power or anything, right, but it is combining a little bit about what we already know and what we expect into our analyses, and sometimes that can let us come to reasonable conclusions, even when maybe, like think about in your work, like there's only so many people that have implants in their brains. Like sometimes there's like really practical limits on our sample sizes. And if we have good information about how something should work, Bayesian gives you a way to formally incorporate that into your analysis and get maybe an estimate that if your prior information is accurate, you can maybe say a little bit more with a smaller sample size.
Yeah, I guess the hardest thing that I run into with power analyses is that often the information doesn't exist, is not published, in order to say there's XYZ effect and it has this effect size, so I'm going to now do my a priori power analysis, and we're going to say that we need 15 people to see this size of an effect.
Yeah.
And it's only become more and more required in writing grants and stuff like that to do these things, and to and I just generally don't like having to kind of flub those numbers, because it feels like most people flub those numbers. They just kind of make it up.
Absolutely. Yeah.
But anyways, although I guess it sounds like priors can be somewhat made up as well.
I think the key difference is that with priors, you have an ability to specify your kind of certainty or uncertainty about it. And for me, that's really key. And I have my small sample size slide coming for you in a minute. I talk about how Bayesian could potentially be used in like pilot or feasibility testing. And I think that's a place where it could be really useful. Okay, so places where I think Bayes really shines, the first of which is in hypothesis evaluation. So in the case where you have a null result and you want to say something about it. The second is, certain unique small sample size scenarios. It's not a universal fix, but sometimes it can be kind of helpful. And then third, in complex models, especially if those models are having a difficult time converging or running into estimation problems. Okay, so start with hypothesis evaluation. So some of you who were around last year might have seen my brown bag before I did my master's proposal. And I'm not going to tell you the details of my master's, but basically I was trying to see if there was a difference in this spatial size estimation task between chronic pain patients and controls. And this was my prediction, that these lines should be different. And the previous literature had suggested that, this was a reasonable prediction. And so I went about my master's, I collected 102 participants. I felt good about my design, and I plotted my data. And it looked like this. Those lines are so overlapping that when I first plotted it, I thought I coded something wrong. Like I was like, there is no difference between between these two lines. So after, reviewing my data, like going through every scenario of what could explain this and checking everything, I felt good about my experimental design, but I just was not seeing the effect that I expected to see. And so I turned to Bayesian as a way to let me evaluate the null and say something about a result that would otherwise just be, well, it's greater than 0.05, so, we can't reject the null. And in doing that, I think one thing that I found to be incredibly attractive and useful about Bayesian is the utility of Bayesian credible intervals. So they are probably one of my favorite things in Bayesian data analysis. And I always like to say they are everything you have ever wanted a confidence interval to be, but it wasn't. In that they give you a probability statement about if the true parameter would fall within a given interval X amount of time. So a 95% credible interval means that the true parameter should fall within the given interval 95% of the time. And I have even done some simulation work with Pascal where I've proved this to myself, like even when I am generating the population parameter, it oftentimes falls within that, it's like 93, 94, it's very, very close. So for example, in my master's thesis in that graph that I showed you before, my 95% credible interval range from -24.5 to 22.2. And you can see that 0 is pretty darn close to the middle of this interval. And those units there are pixels on a line task. So what this told me is that my effect, the true parameter should fall within that interval 95% of the time. So I have a pretty high amount of certainty that if there's an effect, it should be somewhere within there. And 22 centimeters, that's like less than half a centimeter. So even if this effect did exist, it is so small that I do not care about it. And so I really kind of valued the way that these credible intervals allowed me to make statements about plausible effect sizes and whether or not those would be of practical significance to me. Another utility of Bayesian in evaluating a null hypothesis can be Bayes factors, which can actually tell you the probability of different hypotheses. I will give you a slight note of caution here that appropriate calculations of Bayes factors are not always agreed upon for all models because you can't always do the analytic calculation for all models. And Bayes factors can be highly sensitive to the prior. So there's some cautionary notes going along with this, but if you can calculate them and you have an appropriate prior, they can be really powerful and useful. All right, so the second scenario I'm going to cover on when you might use Bayes is small sample sizes. So like I kind of talked about earlier with my Wyoming example, building in prior information can be really useful, especially when you have very few data points. And I kind of think about it as sometimes like the prior puts some guardrails on so that if I only have a couple data points, I'm not going to conclude something that's like wildly inaccurate because I can use my views and my expertise in whatever I'm studying to think about like what would be plausible or reasonable for me to expect. So with appropriate and informed priors, a Bayesian approach can allow you to do more with a small sample size. So one example is that any of you that work in structural equation models, there's some papers showing that Bayesian structural equation models can run with less than 50 participants, which if you work in SEM at all, usually it's hundreds of participants kind of data technique. So there are a lot of caveats here about your prior has to be really good. And there's plenty of ongoing debate within the quant literature about this. But the fact that these run and give you reliable estimates, given you have an appropriate prior with that small of a sample size, is pretty cool. And I think Bayesian can be especially useful when you're working with hard to recruit populations where increasing sample size is just like not possible. I mentioned this earlier, but I kind of think about both Corys in our group in this context. So, you know, Corey, faculty member Corey, you work with people with IEG, and there's just not that many people that have that. And my lab mate, Corey, oftentimes looks at, like, you know, thinks about populations with really interesting sensory issues. And there might just be a limit on the number of those kind of people you can recruit. And if you can have some well-informed priors about what might be happening, I think it's a way where you can, you know, make some reasonable assumptions with a smaller data set.
Yeah, and I will say, you know, like there are whole, you know, animal models that, you know, often their papers are published with 2 animals, 2, maybe 3. So with non-human primates, like electrophysiology studies in non-human primates are often done in just a few animals, and they have to think about things in a very different way. So a lot of my exposure to Bayesian statistics has actually come from that you know, reading that literature, things like that.
Yeah, absolutely. And I think that's the cool thing, is you can build in some of maybe that prior information from how the brain should work, and you can still, not be super certain about it. And your prior doesn't have to have a ton of influence, but you can have a way to give your, I think of kind of giving your sample a little more to work off of.
Yeah, I have 2 comments or thoughts on this. One is that it seems like with Bayesian that you might be able to more easily combine results across papers by like data sets are more easily stackable to some extent. Like for instance, if you were to do a meta-analysis on a bunch of papers that had used, let's say for instance, everybody had used Bayesian statistics and never used a frequentist thing, for say you're doing a meta-analysis on some certain domain, it seems like it would be easier to put all that information together. Or I guess to some extent, you're almost, your prior is kind of the information you would take from a meta-analysis to inform your, or at least that's a form of data that you could turn into a prior.
Yeah, absolutely. And I'm actually not familiar with Bayesian meta-analyses. They probably exist, and I'm sure there's methods around that, but I do think that results from some sort of a meta-analysis are kind of nicely incorporated into a Bayesian framework.
My second comment actually relates to that, and that is, the status quo of so many people using frequentist analysis and not being the concern about a reviewer not being familiar with, how Bayesian statistics are reported and things like that. Like, do you have any thoughts on that, and like how best to work around that? Because that would scare me off from doing a Bayesian statistics in a domain like a statistic or like a research domain that doesn't already have a rich history of using Bayesian statistics.
Absolutely. I think you have to be a much better science communicator if you're going to do Bayesian statistics. And you have to spend a lot of time doing that. And I can't speak directly. I have some stuff I'm writing up doing Bayesian, so I can tell you once I've gotten reviews on things what that's like. But I do think there is more of an onus on you to explain what you're doing, why you're doing it, and how it's advantageous in the scenarios. So anytime you're doing any of these things, I think you are fighting a little bit against the status quo potentially.
I had a little comment related to that because it's an interesting thought. First, I thought this might be a good time to plug our Bayesian mixed models reading group, because we're reading a book that goes over best practices for exactly doing those things, practicalities, reporting in cognitive science. So if folks want to join us, you should. But the second part is that I actually wonder how much the opposite problem will begin to rear its heads as these methods are being applied more widely, which is that without consistent reporting guidelines and with people who are kind of just starting to adopt these methods and kind of, sort of learn and then immediately apply them and then go to try to publish them, at least in my experience, peer review has not been a good filter for it. You actually get sort of the opposite reaction many of the times, which is rather than coming at it with extreme skepticism, people kind of go, oh, well, they seem to know what they're doing and this isn't my thing. So there's probably a reviewer on here who's a stats person and I'm not gonna, go with that. And as a result, at least in the prior wave that we've seen this in my field, which is the, application of complex frequentist linear mixed models, there's a lot of mistakes in how the models are set up and how they're interpreted that get all the way through to publication, in part because there aren't enough people in the field with that knowledge of best practices, and it's been referred to a little bit as letting a gorilla into a into like a what's the phrase? Letting
like
off
a bull in a china shop kind of thing?
bull in a china shop.
Yeah.
That's it. Yeah. Thank you. I had the wrong prior there, the gorilla. I think this is only going to be a compounding problem in our field as we introduce even more complex models, especially where, as I don't know how much you're going to get into this, Miranda, maybe now or later, decisions on the behalf of the analyst play a very big role as you get into more advanced Bayesian statistical models. So I think we need to be careful in how we educate folks in using these tools, probably at a really early level.
Yeah, absolutely. I mean, you see this happen with, like, I saw a paper recently on SEM and how, like, there was a bunch of papers where the fit statistics were like literally impossible. They're like reported all over the place. So I do think, like, any new method that a lot of people are adopting has these risks, and it's more, I think, responsibility on you as a scientist to make sure you feel good and confident in your results, and you're not relying on peer review to, like, catch things for you, and that you're being thoughtful and informed about how you go about these things.
I will say, as a reviewer, I mean, anytime I run into something that I don't understand, I ask the editor to bring a stats consultant in on that particular, like, if I think it's a little fishy or I don't fully understand it, that's when I ask them to bring a stats consultant to just specifically read through the statistics and see if there's anything that doesn't quite jibe. Like, usually I'll have some understanding of it, but not necessarily fully be able to describe exactly why I don't think it's the right way to do X, Y, Z.
Yeah, absolutely. And, there's a limited number of stats people that end up on peer reviews. So it's definitely a problem to grapple with, especially as our statistics become increasingly complex. Okay, so for the sake of time, I'm gonna skip to the next slide here, but I do kind of just want to highlight that in small samples, the prior has greater influence. So, really thinking through your prior is especially important. And that's really going to be a key component if you're applying this in a small sample size context. All right, so the final scenario where I've seen Bayesian be really useful is in estimating complex models. So I find that Bayesian approaches sometimes can make easy things a lot harder. And if you're just trying to do a linear regression, you have to do priors and there's all this stuff. But oftentimes they make hard things, hard models that are having trouble estimating and don't want to converge a lot easier. And sometimes I've seen convergence issues be solved in complex models like MLMs or SEMs, sometimes even just by popping over to Bayesian and using a non-informative prior. So it is really, I think, a powerful tool to potentially solve for models where the complexity is important, theoretically or otherwise. And we want to be able to solve those models and make sure they're giving us good estimates. And then I have also found that if you can put even like minimal constraints on parameters via your priors, it can lead to like much better estimates, especially in the context of complex models. Pascal and I are working on a project, and where we had done something in a frequentist like SEM context and have taken a Bayesian estimation approach and are doing a simulation study, and the estimates are great. It's really like, it performs really well if you can put even like minimal constraints on what might be values for your parameters that are just completely absurd. Like that beta is not gonna be over 10 or whatever in this scenario. So it can be really useful. And I think about it as giving, we can use our prior knowledge sometimes to give our models a little more information to work off of. Brennan, did you have a comment?
Oh, no, I was just going to totally agree with you. And that was sort of the reason why I've decided to finally get drug into the, into this after kind of avoiding it my whole career, because when we were fitting complex mixed models for an eye tracking experiment recently, this was with Ryan before he left, models with, complex random effect structures, lots of random slopes going on. We're just in LME4, we're failing to converge over and over again, which is super common and causes this problem with having to kind of do this hacky backward model selection thing where you end
like,
up with,
throw that random effect
just
out.
the, a model that's obviously overfit, but just fit enough to, at least converge. And we fit those same models with BRMS using completely non-informative priors, and model converges no problem, and it has sensible parameters for the random effects, which is really nice.
Yeah, absolutely.
Just to clarify, non-informative prior is that uniform distribution?
Yep, you're just doing that flat guy that's negative to positive, or whatever your values are that are possible.
Wait, why I'm not quite grasping why that would work almost the same, if the same model is not converging in another framework, why would adding a prior that doesn't have any information in it actually help to make it converge?
Yeah, so this is a good question. And to be perfectly upfront, I am not entirely certain of the answer, but I would guess that it would be they're using different ways to estimate. And when Bayesian, it's using it's like a simulation sampling approach using Monte Carlo Markov chains, and that probably gives it an advantage. But if Brennan or Pascal has any idea and wants to chime in on why that exactly works, feel free.
We can also talk about it offline. That's just a hole that I'm not quite.
Yeah, it's surprising. I've also
short answer is frequently with these where you run into these convergence problems, they're in the random effect structure of the model, where you're trying to estimate a variance covariance matrix of, say, your intercepts and your slope effects across subjects, across items, and you just don't have enough data to actually estimating all those, and you end up with these solutions that aren't real, that can't be possible, like a covariance that's larger than a variance, or a negative variance. So you're estimating something right at the border of what the parameter can be, and within a Bayesian framework you can kind of regularize those and do some nice properties to kind of just say, okay, that thing is, you can just assume is basically zero, and you don't run into these problems under, like with LME4, where that just breaks the model from continuing to converge. That's my clunky knowledge of it. I'm sure Pascal has a better, could have a more articulate version of that, but that's been my experience, at least my limited experience with it.
I don't think I have any better answer than that, Brennan. That sounds like what I would expect. I mean, the only other thing I could imagine looking into the code is that while giving uninformative priors for the variances, you probably didn't actually specify the variances to be allowable from anywhere from 0 to positive infinity.
Right.
Which technically the frequentist framework would say anything from 0 to positive infinity is equally likely. So even cutting off at some point and saying the variance, of our random effect probably shouldn't be exceeding the variance in our data or something like that, puts a cutoff point that doesn't exist in frequentist statistics. So there's kind of information there, but not, it's not real, like saying that a variance number should be less than the variance in the data isn't like really information, but it actually does help with convergence for some. I was complaining to Marinda the other day that my intuitions around this like why that is enough to stabilize some of these models. It's just not completely intuitive to me. But it does seem to often help quite substantially.
It's very interesting.
Yeah. And I think the priors by default in some of these, like we use BRMS kind of a front end for Stan that handles some of this for us if we want to use the non-informative priors as a starting place. And they're not uniform priors. You know, I think for the variances, it's like a half student teach distribution. So it's, you know, truncated at 0, can't be negative, and then kind of follows, you know, lower values are more likely. And so there is information in those. They're just, it's not a very strong constraint, but it's more information than in the frequentist model. And as a result, I think the model can converge with less information there.
Yeah, you can give it like very little information and it helps a whole lot. It's surprising sometimes how much it can help. But okay, in the sake of time, I'm gonna kind of truck on here. So to conclude, hopefully I've answered all these questions. So what is Bayesian statistics? It's a statistical framework that formally incorporates prior beliefs, which are updated as data are observed. Why might you bother with Bayes? You can do or say things that would otherwise be unfeasible or potentially impossible in a frequentist framework. You can talk about hypotheses and parameters probabilistically, which is really useful. I really like this quote from Roy Levy about Bayesian that says, with Bayesian, you can say what you mean and mean what you say. And I think it's just a really useful way to expand your statistical toolkit. It is a bit of overhead. I'll tell you that right up front, but it can, I think it does have quite a few benefits. And then as far as when you might use it, hypothesis evaluation, it really shines in certain circumstances where you might have a non-negotiable or purposefully small sample size. And then in complex models, especially if those models are struggling to estimate or don't converge. Okay, so I'm going to leave you with a tiny hint about the how. So there is this programming language called Stan, which makes Bayesian models a whole lot faster than they were before. And there is a BRMS package that Brendan mentioned briefly by Paul Berkner, who is actually a Stan developer. So is very intimately familiar with the Stan language and has created basically a way to interface with Stan while providing where you're not having to write your own code. And Brennan the other day put it in a way that I really liked, is it's like at the bowling alley when you have bumpers on, it gives you some bumpers on doing Bayesian analysis, and that you there's a little less room for you to kind of make mistakes in certain areas. And it just makes running the kind of statistical models that are really common in CNS, like our mixed effects models in a Bayesian framework, very accessible. If you would like to dive in and learn more, you want to take it a step further, or you want to think about maybe writing your own Stan code, I have really enjoyed the Doing Bayesian Data Analysis book by John Krushke. I will also say that it is Dingo's favorite Bayesian data analysis book, but it does have puppies on the cover, so I don't know if the rest of the books really had a shot. Anyways, I want to thank you all for your time and attention and all the comments and questions you had throughout. I know we're close to time, but I am happy to stick around and answer any questions or listen to any comments that you may have.
This was great, Miranda. Thank you.
Yeah, absolutely.
This is definitely the best I've understood it.
Okay, good.
I feel like I've stared at Bayes' theorem a lot of times before and not known, like I've been able to apply the simple things like, probability of, I've used it with, probability of my baby being, like my wife's or our baby being, having some disease based off of the information that we've gathered from imaging and other things and the likelihoods and all that stuff. Given the data, but this has been really great.
Yeah, it is a little bit of a jump from like the neat discrete probability things to how we're actually doing this. And there's a lot of stuff behind the scenes, like, you kind of Bayesian will force you to maybe adopt some computer science skills and think about, Markov chains and things like that. So
we're all having to do that anyway.
there's a bit of a jump, but I think that it's something that holds a lot of promise, and it's kind of cool to see what it can do. All right. Any other questions I can answer?
That was really great, Miranda. One thing I was just going to say, like from kind of editor point of view, right? Like we're seeing, I think what we're seeing in like traditional cognitive journals where people are used to doing ANOVAs and then, somewhat MLM now, is that you see Bayesian used for your first option that you were talking about, like somebody gets a no difference in their effect, and then they do a Bayesian analysis to kind of interpret that null hypothesis, and or reviewers are asking them to do that, right? Like so, and I think that's like looking kind of more, kind of accepted. Whereas at least from what I've seen, I haven't seen like further kind of just pure Bayesian analyses done like as much with MLM or something. But I think maybe that's coming, just like what we saw. I feel like Brennan, mentioned this, like there was a trend, there was this initial like movement to do multi-level models instead of ANOVAs, like, and you kind of would see that and people not, being clear about what they were doing, or reviewers like not really liking it because they didn't understand it, or it wasn't communicated clearly by the authors. And I feel like that's changed somewhat. Like we're kind of starting to see like just like multi-level models are pretty accepted in many of these kind of mainstream journals. And so maybe we'll see that more with the Bayesian modeling too.
Yeah. And it comes with a lot of the same problems, like Brennan was saying. You can definitely go off the rails with Bayesian. It can, it can go wrong very, very easily. And there is, quite a bit of context that needs to go in and be thoughtful about how we're applying these.
Yeah, but you can definitely do like the combination, like I think what you did in your master's thesis, and like we're seeing these examples where like people do the frequentist analysis and then just add on a Bayesian analysis to show a Bayes factor that is going to support, their claim that there's really no difference in this effect.
Yeah, absolutely. And especially when they come to the same conclusion, which was like very, reaffirming for me when I like did my Bayesian analysis and it was like identical. It gave me, a little more confidence, and then just a way to talk a little bit more about that zero effect in a way that I can't really do in a frequentist framework.
Mm-hmm.
All right, well, we are narrowing in on 5 o'clock. So anyone who wants to hop off, go for it. I will stick around if anyone has any lingering questions. Always happy to chat about Bayesian. So I will stick around for a minute, but I appreciate everyone's time and attention, and I'll see you all next week.
Great job.
Thanks.
If anyone wants to stick around, we did have a couple questions for some students that you might be able to give us some feedback on.
Sure.
For the we'd like to put together a kind of CARE / Utah swag package for the prospective students that we're inviting. Just something that we can send them potentially. And I don't really know exactly what we should send them, or should we just go to the bookstore and grab stuff? Like, what do you guys think you would have liked to see? Skis. Nice. Well, maybe we can give them the option of either getting skis or coming to visit. Or just one ski boot, maybe. Any other one ski each? There you go.
I'll just throw out there, I found out from School of Computing is doing this for their computer science accepted students, and they are sending